Hello, welcome to this new lecture of the Locomotion and Haptic Interface module. We will talk this morning on one of the devices which are available in our robotics lab. I will describe more in detail what this haptic interface, the Geomagic Touch, is made, how it works, what is the software, and then I mainly devote the rest of this presentation to its application. Most of these applications have been developed in our robotics lab. The preparation of these slides, which is an expanded version of what we used to have on the website, has been made thanks also to the contribution of Marco Ferro. So, essentially this is the haptic interface Geomagic Touch. It's a very compact desktop device, so it stands near to your computer, to your screen. It has an articulated arm, very light, and it can be handled with your hand by holding these sticks, which contains also this form of a pen, which contains also two pen buttons for modifying its operation. We bought one of these devices a few years ago. It was, let's say, 7 or 8 years ago. Then we bought also a second. The commercial cost of this device in its basic version is around 5,000 euros. Now, the story of this device is kind of complex because you can, now we call it Geomagic Touch, but in fact it used to be the Phantom device by Omni, which was produced by Sensible Technology. You see on the left side more clearly the brand name of the same device. This has been acquired in 2012 actually by the 3D systems, and now you can find on the market both devices with different colors, different aspect in fact, but in fact they are the same, the one and only device. So there are a number of degrees of freedom, and so we have also this articulated structure that can rotate around the first axis, can elevate the shoulder, can go up and down with the elbow, and these first three joints are in fact actuated. So there are motors that can move this joint. But in fact, the motion of this joint, as we already said, it's not really interesting because it's the human user, the operator, that will move the entire structure. At the end of the second link outside, so it would be the third link in a Demerit-Artenberg notation, there is a point which is called the haptic interface point, which is very important because we will map this point into some virtual agent in a virtual environment or in a physical point in a remote real environment. The size of the structure is clear from the bottom picture. There are 13 centimeters of height, 30 centimeters of length of the first link, and then 13 centimeters for the second link. And on the pen there are two, as we mentioned, two pen buttons, and if you press one or the other or both of them, as I said, you can implement different features. There are 3 more degrees of freedom in the pen. In fact, at the end of the second link, where the hip point is placed, this is also a center of a spherical wrist. This is more clear in this second image. Again, this is a different color, but it's exactly the same devices. As we said, the first 3 joints are actuated, so the motors are inside the base, and there's a transmission in the structure, while the last 3 joints are passive, so joint 4, joint 5, and joint 6. As you can see, one joint is a rotation around the second link, then there's a second rotation around the hip point, and finally a rotation of the pen in the direction pointing to the hip. So in fact, the last 3 joints at the hip constitute a spherical wrist, and they are fully passive, as we mentioned. This is the data sheet of this device. It is important. A few numbers are more important than the other. First of all, the first data, 160 times 120 times 70 millimeters, so it's a parallelepiped, where the device is rated to provide force feedback to the user, so to the hand of the user that is holding the pen. The weight is also important, about 1.42 kilograms, so relatively large. It's to be specified that this interface, haptic interface, is able to provide only force feedback, so force in the 3 Cartesian direction, x, y, z. And this is possible only if you are restricted in the force feedback workspace area. Despite of this, as we have seen, there are 6 degrees of freedom. The last 3 are passive. More important are the numbers which are contained in the red boxes. So the maximum force that can be exerted in a special configuration, which is 3.3 Newton. So let's say about 30 kilogram of weight in different direction. And the other important aspect is how this feedback, how this device shows stiffness. So in response to a modification of 1 millimeter, it is able to apply a force of 1.226 Newton in one direction, 2.31 in the other direction, and 1.02 in the along the z-axis. So this is the stiffness, the apparent stiffness that the device is able to produce. Another important aspect are the resolution. The resolution is given by encoders and potentiometers. We can generate velocities from subsequent measurement of this angular position sensing, but of course there will be some noise because the accuracy is not that large. This device can be interfaced through Ethernet port or USB port, and of course it comes together with software, basically with the OpenHaptics toolkit, and we will describe this later in more detail. So let's see this device in action. This is a video taken from the YouTube, and you can see here that it is used as really a graphic interface. You can have a library of objects, you can move them around in the workspace, and by taking virtual tools with buttons and with the mouse or the keyboard, you can carve objects. So this user has started with a cylindrical object and now is using this tool to eliminate some material. And of course you can assemble, disassemble, combine, and do another long list of action on this virtual object. You can change the point of view and so on. All this is part of the software that comes together with any of the haptic interface of the Geomagic, not only the Touch X, and so on. You have just to specify which device you are using at the lowest level, and most of the routines remains the same. Of course, for interfaces which have the capability of returning 6-dimensional force feedback, so both force and torques, there are more features available. So here we see another couple of video that illustrates how this interface, haptic interface, can be used and who is using this. Of course, artists and industrial designer, or professional, in particular in medicine. There's a huge amount of activity there, and of course more in general researcher. On the left video we see that you can move the interface to pick up a color and then write something on the wall, and of course all this this environment has to be created, and there are primitives that allow you to do this. Or you can use the interface to modify some shape by applying forces and letting the material modify accordingly. Or you can use this to inspect an object, to disassemble or reassemble, to move around parts and look at this, look at them from a different point of view. Again, you have to use the interface in a flexible way. Again, here is a similar application as the video that we've seen before. You use the agent which is associated to the hip point that you move with the hand, so moving the hip around with your device, and this corresponds to the black sphere which operates here by material removal on an object which is rotating. Again, the fact that the object is rotating and you're removing voxels by drilling in this sense has to be programmed as the application dependent part of the system. So many applications, as we have seen, touching, modeling, painting, carving 3D shapes. You can plan surgical intervention in a virtual world. You can navigate in a virtual world that you reproduce in your graphics scene, but you can also be interfaced to real devices like robot. In this sense, in this case, we talk of teleoperation and control of teleoperation, possibly through channels which are affected by delays. You can coordinate robot teams, for instance, a team of UAV, as we have seen in the first part of this of the lecture of these modules. So here, for instance, you can see the setup that was developed, in particular here at the University of Roma in collaboration with the University of Napoli Federico II, so Sapienza and Federico II. Here you see two haptic devices and the user wearing a head-mounted display, in fact an Oculus Rift, and on the other side, in the picture inside the video, you see this well-known Da Vinci surgical robot, which is made up of 3 different arms with both revolute and prismatic joints operating in a scene. And here you can see how by moving both interfaces you can move around multiple arms, taking into account the different kinematics between the master and the slave in this remote virtual world. We have seen this slide before. It's is in fact the full haptic rendering control loop. So the human operator moves the device, the configuration is being sensed by the sensor for both joint level and then Cartesian position of the hip. Through the forward kinematic, we map the hip point or whatever virtual tool associated to the device in a virtual environment. In this environment, we may have collisions, so contact, and we have a model for generating force. There are many models for generating forces. This force is transferred to torques at the level through the same Jacobian which appears in the forward kinematics of the haptic interface. These torques are being amplified and becomes current for the motors, and this is the feedback that you feel on the handle by the user. Of course, three-dimensional in case of the Geomagic Touch, six-dimensional for other more complex and more expensive actually haptic interfaces. So the generation of feedback is made by a geometric model. Again, the most simple case is that you have a force generated by a simple spring or a spring and a damper. So while moving your hip inside some virtual object, you compute the closest point, so between the real avatar position, which is inside a virtual wall or a sphere like in the top figure. You compute this distance to the ideal avatar, which stands on the surface of the object, and this deformation is multiplied by a stiffness constant, which you model for the spring, and you have a reaction force in the direction from the real avatar position to the ideal avatar position on the surface. Of course, if the surface is smooth, finding the ideal avatar position on the virtual surface is relatively easy. If you have discontinuity of tangent, like on a cube, when you're close to a vertex, you will have some uncertainty on that. So some discontinuity in force generation. This has to be filtered in order to give, or not, if you want to give us a feeling of this discontinuity to the user. Of course, the same applies for a real environment. In this case, the force needs to be sensed remotely by a sensor or estimated by different means based on the geometry, based on vision, based on internal information. For instance, we have used in robot manipulators, if you have taken the course of Robotics 2 already, or if not, you will see it in the course of Robotics 2, the generation of model-based residual, which estimate the contact forces, and sometimes can estimate very well the contact forces if we know in advance the position of the contact point. So in both cases, in virtual environment, in real environment, we are generating the force in this way, and this force is then transmitted to the master device, so to the haptic interface, to the Geomagic Touch, and rendered in terms of a force applied to the human operator. Now, there are many sources of forces. For instance, there are friction forces. So when we are in contact or where we are in special area of the virtual environment, we can feel a force while moving in contact. There could be static or dynamic friction forces. For instance, in this case, suppose that we are applying a normal force to an object, and we would like to move according to a tangential force. Now, if this tangential force is smaller than the static force, we cannot really move. So we are in a stick situation. And this static force is proportional to the normal force that we are applying. So the more we apply force along the normal, the higher is this force. And if the tangential force that we would like to apply does not overcome the static force, there will be no motion. As soon as this is being overcome, still proportional to the normal force, we have a dynamic friction force which opposes motion with a dynamic coefficient equal to mu d. And typically, if the static friction coefficient mu s is larger than the dynamic friction coefficient mu d, we may have what is called a stick-slip phenomenon. So we apply a force, but we don't move. All of a sudden, we overcome the static force, and we start to move, but this we have an opposition of a smaller dynamic friction force. When we reduce the force, for any reason, the tangential force, we may fall down back into the static domain and the system stops. So we have a stick-slip phenomena, which is kind of annoying, and in real world is actually something that we try to avoid. So there are many modeling possibility for friction forces. There are other forces that can arise due to the fact that the avatar, the haptic representative of your hip point is attached or is close to an object. So if it's close enough to an object, it may grasp or grip the object and feel its mass and inertia. So when we are moving the tool at this point, we feel this heavier dynamic force. So we feel the mass of the object, in fact. This is, of course, purely virtual. In the real world, if the end effector of a robot grasps an object, of course, if we have an end effector force sensor mounted on the wrist, we can feel this force and let this force being felt in the distance to the user. So, as I said, this force effect either arises from motion, because we are moving in contact in some area of the virtual space, and could be friction of the various effect. We mentioned already the stick-slip effect. We can also induce a vibration. For instance, if we're getting closer to an area, or if we're getting in contact, or if the virtual object is feeling the force, we can render this force through a vibration effect on the haptic interface. And there are other forces which arises or that are generated because of the presence of what are called virtual fixtures. So geometric shapes that are used to guide essentially the motion of the virtual avatar representing the hip point in the virtual space. So this is particularly important, for instance, in surgical robotic application, so both virtual and real, because this virtual fixture help the surgeon to stay on the path or on the region in the area, or to approach a point in a very, let's say, stable and vibrationless way. For instance, if you have a cone, a virtual cone, and you're entering in this cone, you're moving and you remain constrained to this cone, which ends up in the point that you need to reach. So any attempt to violate this constraint, this virtual constraint, these fixtures, in fact, will result in a generation of force which opposes this direction. So you will have elastic forces or very stiff forces being generated, or even just viscous friction in some forbidden direction, so that you can feel that this is not the appropriate way to go. A surgeon that is using a haptic interface to drive its surgical tool remotely don't like too much this type of information. For instance, don't like to be constrained on a given geometric path that has been planned for the tool, for the remote tool, to enter the human body. So the stiffness of this path, of this virtual path, of this line or surface or cone that it may be modulated. So if you have a very expert surgeon, you would like to allow some deformation, some deflection for this geometric path, because he knows what he's doing. If you have a less experienced surgeon, you may wish to be more stiff in this guidance of the remote tool, and things like that. There are, of course, a number of aspects which are important in terms of ergonomy and of psychological impact of such an effect. But this is another way of which is very much used in order to help through the haptic interface the task operation of a surgeon, and not only. So more in detail, how do we generate these signals? This is taken from a lecture by Alessandro Okamura, this slide. So if we have at some point generated a desired force, so we have some levels that we can have because we have a digital data. We convert this digital data into an analog, so we have volts through which we drive an amplifier, which brings these small signals to the level capable of generating motion with the actuators. And the actuator stores through the transmission and reduction and the kinematics of the haptic device turns out to be an endpoint force, for instance in our case a 3D force, in some other cases also in a 3D torque applied to the endpoint of the haptic interface, so to the human operator. This is only part of the rendering because side by side with the haptic rendering we have learned that there is a visual rendering also. So the haptic device has bidirectional effect and the human operator sends velocity, position or force command through to the simulation engine if we are talking about virtual environment, and the haptic rendering in this simulation engine returns forces to the human operator. From the simulation engine, for instance, in the reconstruction of the ancient Pompeii in the Cyberwalk project, we have also the possibility of having visual rendering, point of views, different point of views, while we move our eyes, our head, if we have a head-mounted display, around, and this produces some video on our device, visual device. And of course you can also include audio if you wish. And in the bottom part of this slide you see how the visual rendering and the haptic rendering work, for instance in response to a detected collision. We have already mentioned that these two loops have different rate. For the visual rendering we can work safely with a 30 Hz frequency, while the haptic rendering needs much higher frequency in order to be transparent and provide fidelity of what's going on in the content. So let's move now to the software part, which is contained in the toolkit which the 3D systems is providing to the user of its set of haptic interfaces. So this is a library of application programming interfaces. It's proprietary to the 3D system. This is the developer edition of OpenHaptics. It's a library of written in C++, of C++ routine, and interfaces all devices of the Geomagic family, not only the 3D Touch, but also the 6D devices, and allows the development of software based, starting from this library and of its feature, for interacting with virtual environment through this device, mainly with virtual environment, not with real environment in fact. The real environment means that you have, for instance, a robot, so you have to develop some routine which interfaces with the robot control in one and in the other direction. There are functions for haptic rendering, for graphic rendering, so for visual rendering of a virtual scene that you can create using OpenGL commands which are interfaced to some macro part of the OpenHaptics toolkit. So there are in fact 3 groups of application programming interfaces which are organized in levels. And the high level, of course, is easier to use. The lower level are more customized to the specific device. So we have the quick haptics, which overcomes the haptic library APIs, and the haptic device AP, which is the lowest let's say layer in this software architecture. So the whole toolkit, we here is the summary, the table of contents of the toolkit, which I will make available on the website. This is version 3.3. Actually, the latest version should be 3.4, but there are no main changes. And you can see the micro API programming quick haptics. There are a number of examples, like creating a shape, for instance, a simple sphere, or putting on the surface of this shape some textures that you can feel, give some motion, prescribed motion to this shape, and many other things. For instance, you can change views, you can have multiple windows open and closed, you can let the object be deformed under the action of forces, you can define different rendering of forces, of different force models, and so on and so on. You can create, of course, an haptic interface. All this belongs to the quick haptics application programming interfaces. There are a library of different possibilities. We will see how to do this, how we can change material properties, or add a constraint on the surface, and so on and so on. And there are a group of programming interfaces which are related to the device, to the specific device, in our case to the Geomagic Touch. So the organization is the following. The whole toolkits, the quick haptics micro API, essentially contains all the common steps which are basic to any application. So all what you need to do, whatever application of haptics and or graphic nature you have. And there are this layer contains mainly 4 C++ classes devoted to different aspects. So the quick haptics properties allows you, for instance, to create shapes, simple or from there complex shapes. It has a list of predefined force effects, for instance, friction models, or elastic forces, or viscoelastic forces, and so on. And most importantly, define callbacks, so the way in which you react, generating codes which are passed to your program in response, for instance, to contact events. And these callbacks may be executed immediately or may be deferred to when this will happen. So this is a very important software structure that you may be familiar with. What are your responsibility in this context? Of course, you have to create some window for rendering the graphics, so your workspace, what you would like to represent. So define the space where the device will operate, the shape of the object in this space with their properties, define where your hip point, where the cursor will be, what type of cursor you can have, what type of tool should move in this virtual environment. While quick haptics will take care of communicating with the actual device, synchronize the rendering of graphics and haptics phenomena, and handle the whole collision. You don't have to handle this by yourself, and this is a good point. So once you have created the environment and you have said where is your cursor and how this moves in response to your haptic interface commands, the presence of contact and collision will be handled by the system itself. So there are 4 classes, main classes in C++. The device space, which determines and defines the workspace of motion for the haptic device. There's a very important class which interface with OpenGL, so changes point of view from different camera, and let interact this object that you have created, this geometric object, with the device. So when you are in contact, this takes care of what happens in the interaction. Of course, there is a class for defining shapes, many one or more objects that live in the virtual scene and how they react in terms of graphical views and surface, illumination, texture, and haptic rendering in case you get into contact with these shapes. And finally, the cursor is the graphical definition representation in this virtual environment of the hip point, which is the endpoint of the second external link of the device as represented in the left picture. And remember that the pen can rotate freely around the hip point as a spherical joint, so you can really have 3 different orientation, including the orientation around the approach axis for the pen around the hip point. This is just an organization of these 4 classes. There are colors. You may not really have enough resolution to understand the details, but in the PDF of the slide you will see this in more details. I can tell you that in the device space class you have force effect on the left, so constant force, damping, friction model, and you have callbacks on the right, and these callbacks involve motion of the object, touch, the use of buttons on the device, the servo loops that you're generating, the type of control. Or in the pink class, it's the shape class. You have, for instance, 3D geometry formats, object, deformation possibilities, and again text and font style on the text, and so on and so on. And of course, you have the cursor class at the end. You have some default or some possibility of modifying this. Okay, so if you go down in the pyramid of the software organization, the next layer is the haptic library interface. So you can create scene using the OpenGL formalism. Again, you can define callbacks for handling events, so collision, or also assembly of object or disassembly of object. This is the level where you define constraints with virtual fixtures, and of course this virtual fixture will use the type of force generation that we have seen in the quick haptics class. And again, here we can decompose what the user has to do and what are the responsibility of this application programming interface. So the user defines, of course, shapes and transformation between shapes. For instance, you can define an articulated manipulator with single body and their connection, how you transform the motion of an object into the motion of another object in the chain. Very similarly to what you do with simulation package like VREP or Gazebo. The responsibility of the library is, again, collision handling. This is the most important, I would say, and also indeed haptic rendering, organizing the synchronization and communication with the device, and synchronization of the various aspects, so that you have full transparency, that the haptic rendering is not inconsistent with your view of the object. This is very important to produce high fidelity in this interaction. And finally, the lowest level handles the specific device. So it specifies what are the forces that needs to be transformed in the device. So these are user defined. It handles the acquisition of data readings from joint position and from current on the motors and so on. So current are related to torques. And you can add here some customized rendering for the specific device, including customized algorithms for collision detection. So this is what is your responsibility at this level, and of course all communication, all let's say data link and medium access, initialization and communication are handled directly by the haptic device application programming interface. So in the toolkit describes also a lot of utilities that the system is able to use, typically vector and matrix operation. So you can define matrices, you can define operation on matrices. For instance, you can do product, inversion, transposition, rotation matrix can be used and applied to vectors. You can extract, you can do the cross product or the dot product between vectors, and this can be done in a very, let's say, general format. So you can do this repeatedly for a huge number of vectors in the scene. Of course, this will require computational power, the availability of graphic cards in order to process this operation in real time. But all what you expect to have is there in the library, so in the toolkit. So this is the overall an overview of the system. So you see the three levels of the toolkit, so the quick haptics, the haptic library, and the haptic device application programming interface. You may have a user interface running in parallel in your environment. For instance, in OpenGL, you can communicate from here, from the haptic device through the toolkit to the OpenGL and then have a graphic rendering, and this loop, for instance on a monitor, or if you wish on a head-mounted display, for instance if you're using the Oculus Rift, or both, and this loop works typically at a rate of 30 Hertz, while the lowest layer of the toolkit, so the haptic device API, takes care of the servo loop, and this occurs at 1 kHz, so at a much higher frequency. This frequency may be the same that a real robot driven by this interface has. For instance, the fast research interface of the KUKA lightweights allows up to 1 kHz of servo loop, more typically 200 Hz, so at the rate of 5 milliseconds of update, and you have to synchronize this with your device, of course. The low-level routines, curiously, are called PDD, where the first P, the P stands for phantom device driver, so here is where the control occurs, and the fact that the phantom name is used while the device is now called Geomagic Touch tells us the story of evolution of these interfaces. So something has been remains buried in the code, like the name phantom. So when you set up the system, first you have to pair the device. You may have multiple devices. In fact, you may have also 2 devices, and pairing occurs by connecting the system to your main PC through an Ethernet cable, or to a USB cable, or through a conversion. And once you have done this, there will be a pairing through IP address between the CPU and the device itself. You have to run a calibration operation which calibrates the sensor, and you do this while the stylus is inserted in the, let's say, in the inkwell. If you imagine that this is a pen, in fact it's not a pen, but the terminology is being used the same. So you calibrate the device before starting, in much the same way as you calibrate or you bring in the home position a robot at start when the robot has incremental encoders. Okay, so this is the same idea. I would start now with some let's say application that you can have. This is very interesting. This has been developed by the group of Professor Pratichizzo in Siena. Here I'm referencing a paper 10 years ago. What was their idea? So before doing whatever application, you have the desire of transparency. So the fact that whatever you do, you don't feel any bias in what you're doing. So here on the left you see an Omega 6-dimensional device. So this is not the Geomagic, but the same can be done in principle for the Geomagic as well. These devices are very light. You see in this case there's a parallel kinematic. This device has 6 degrees of freedom, but here is being used only in position. And they are light, but if you leave the device by itself, the device falls under gravity. So when you're holding the ball, which is the effector of your haptic interface in this case, or when you're holding the pen, in the case of the Geomagic, although light, you will feel some gravity. So if you want to move and apply a force in a certain direction, the actual force that you feel is, or if you feel, let's say, a force applied by the device to your hand, you include in this total force, so the Fh in this case, also the gravity, so their own mass of the device. So the idea is, can you compensate this? So apart from the kinematic calibration, can you self-calibrate the system so to eliminate completely the presence of this gravity? The bottom picture on the left shows that if we apply an additional, through the motors of the device, an additional force at the end effector, g of x, depending on the position, which fully cancel minus g of x, which is the gravity effect, then the haptic rendering will be completely transparent, completely high fidelity will be realized, because the actual force is equal to the haptic force once you have cancelled this. How this can be done? They developed an offline self-calibration, so they move the robot in different Cartesian position under the action of a PD control. The PD control is not able to cancel gravity, but at steady state you will have an error, and you can use this error to update a feed-forward component. This iterative scheme for learning gravity is something that we developed in our department many years ago, both for rigid and as well as for flexible structure, joint elasticity or link elasticity, and this is contained in this paper of 1994. So they're using this idea of iterative learning scheme of gravity for each of these points. They divide the workspace in a grid of points, and they repeat this for any x position, let's say. Once they have done this, they go online. So at the online time, they compensate gravity depending on the configuration. And here is a short video, I guess 90 seconds more or less, where you can see this offline calibration on the Omega device and then on another device, and this could be also repeated on the Geomagic. Actually, this could be also a subject of a short project in this LHI module. So you see that they move around, and on each of these they change orientation of the device. Now they have put it let's say vertically, and they repeat the same thing. They change device. You could do this for any device. You see that the object is now brought to the position by the PD controller, although not accurately, and then it learns after some iteration what is the command that should be given to compensate gravity in that position. And then they change the base orientation of the device, and they repeat the same. So this is the offline self-calibration procedure. And indeed, you may also put the device on an inclined plane and repeat the same. You can do whatever experiment. And now the online phase. So you see that the object is not falling if compensation is made, otherwise it would fall under its own gravity. If it's not falling, you can move around the system as you wish. Again, here, with the compensation, the robot remains in place and can be moved without any feeling of the force. You see here that the gravity will bring the device to the bottom, while if you turn on, the user has done this through the keyboard, the online compensation, what you have learned, you can, same story in this other situation. The device falls under its own weight, while with online compensation now, after the offline calibration part, gravity is completely cancelled from the picture. This is the inclined situation. Okay, when you switch off the compensation, the system falls down. Okay, so this was work performed by the group of Domenico Pratichizzo, very active in the haptic world and robotics as well. So let's move to a very important aspect, an aspect which is important especially if you would like to develop the application interfacing with a simulator, a robot simulator. So this is a main use of the Geomagic for robotics. So you have mainly our preferred tool is VREP. VREP was developed in 2010, the first release. Very recently has changed name, now has become Sim. In fact, VREP itself was developed by Coppelia Robotics and now has become, let's say, the main product of this company, so they decided to change the name of the software to the name of, including the name of the company, so Coppelia Sim since 2019. Nothing has changed essentially. There's a freeware version for educational, which has some limitation, but no major limitation for our purposes, so you can really use Coppelia Sim as you were using VREP before. So what does VREP do? It's a very versatile simulator. You can program robot motion and also program controller. You can work at the kinematic level or you can work at the dynamic level. Most of the time we use VREP as a kinematic animation of what's going on, unless we have to handle with collision, exactly in the same way as the toolkit provided by Geomagic. So the haptic APIs allows you to handle collision in the virtual world generating inside. Now we would like to be interfaced to this environment. Why? Because in this environment we have a number of predefined robots, or we can generate new robots in VREP, and so it's very friendly from the robotic side point of view. So VREP itself, in fact, has a number of control entities, plug-in C++, it can use ROS nodes that have been programmed in C++ or in Python. It has application that connect to other clients like MATLAB, so we can make a simulation in MATLAB and have only the rendering in VREP, and so on and so on. Now, all this makes it feasible to interact also with Geomagic as an input device and also an output device for rendering forces, and of course with the whole set, through that, with the whole set of OpenHaptic libraries. So it's convenient to have this interaction. So how do you interact with this? So this is a chain of things. So you can start by moving the haptic interface, so the pen, you're moving the hip, so you send the state of the hip, the position, and maybe also the velocity if you wish, to the VREP control entity, which will update whatever tool you have attached to the hip in the virtual world generated with VREP. So if you're moving around this, for instance, you detect a contact, here the green sphere going against the KUKA cube, so you detect collision, and in fact you can detect collision using the VREP feature, or using your own software or whatever you wish. You compute the virtual force, and this force is sent to the device, and you impose through the actuators this force to the human user. So this is the full haptic rendering loop. Of course, you may have also visualization in VREP, so you have also a graphic rendering, and you have to synchronize this, and this is a matter both of the Geomagic Touch side and of the VREP side at the same time. So the control entity in VREP should be whatever you do should be responsible of the communication between the touch device and the virtual scene, and communication includes also coordination in one direction and in the other direction. You have to couple, of course, the HIP, the interface, the haptic interface point on the device with a virtual object in the scene, and this pairing can be changed, so this couple needs not to be permanent in a given application. In this case, it's the green point which has been paired or coupled. And as I said, when computing the feedback force, you can use the VREP collision detection module, and which is built in, or you can define your own routines in order to generate the virtual force. This is very convenient indeed. So the VREP, as I said, the VREP control entity, which is something that you should program, in fact, already exists. There is a so-called, I don't know how to pronounce it, this is CHI 3D, so it's computer haptics and active interface in 3D, which is a VREP plugin which does this handling of all the communication and interfaces and exchange of data. So the child is again a multi-platform, so it's not only for VREP, but it has a VREP plugin. It's a multi-platform library of C++, both for visualization and for haptic interface. In this sense, it can wrap around the OpenHaptics library, so it just, let's say, a software level that allows to communicate without extra effort with all the classes and programs and C++ routine of the OpenHaptics libraries in a seamless phase. So you see that inside the Child 3D libraries there are also the haptic library APIs of the OpenHaptics, and also the haptic device API. There's an extra L here which should not be there. So it handles, because it's not only haptic, it's also graphics, so it manages graphics based on the standard OpenGL, and allows getting data from the device and setting values, for instance, of current for the motor values in an easy way. And as I said, all these properties are integrated in a module which is designed for VREP, and it's a plugin for VREP. It's again a C++ plugin. So very good, so this helps a lot. So if you work with Chai 3D, you can use all the features of this. There's a limitation. Apparently this has not been maintained, and the latest VREP version, in particular the latest SIM version, when the system changed name, are no more compatible with some or all of this activity. So in a sense this is obsolete and needs to be revised. Either Child 3D will revise itself with the latest Coppelia SIM version, or you have to do your own VREP plugin by yourself. But before being obsolete, we have developed a number of applications using this. For instance, this was one LHI project, short project, probably made in collaboration with the MedRep, the Medical Robotics course. At the end of this slide you will find a full reference to this student project, so if you're interested I can provide you some of this. So here they developed a simulation environment in VREP intended for a task which is important in medical robotics, which is the needle insertion. Not only the needle insertion, which is a pure motion problem with many specialties, however, but also rendering the force that this needle exert on tissues while entering some body, some biological body or human body. These forces need to be sensed and rendered to the user, which is moving the VREP robot, so in this case the KUKA LVR4, through the Geomagic interface. So child is synchronizing the simulation loop in VREP and the haptic library of Geomagic, and of course also the low-level device interface. So let's see what's going on here. You see a generic environment, a free environment, the KUKA robot, the classical orange color, and on the end effector there's no force sensor mounted, but there's a 120 millimeters long, more or less, needle mounted, fixed to the end effector tool. And you see on the right another view, a side view. You can see the red point, which should be the tip of the needle, and you see here two plots where you will see signals passing through these signals. The lower signals is the expected contact force at the tip, so we know that we enter in contact with the environment with the tip of the needle. While the needle enters the surface, there will be also friction, because of friction that changes depending on the tissue and on the interaction between the needle material, which is the needle material, and the type of tissue. Here, I'm not sure if in this video what you will see are also the so-called residuals, so an estimation of the force arising at the contact moved to the joint of the robot. So this can be computed only based on the model, and from there, knowing the contact point, so knowing the kinematics, the direct kinematics, and also the geometry of the needle, so its length essentially, we can reconstruct also the contact force at the tip without having the sensor. Note that even a force torque sensor mounted on the end effector, virtually or in reality, because of course this work has been moved later on to the real world, so even having a force torque sensor would not tell us exactly what are the forces at the tip or along the needle while passing through biological tissue. Okay, so let's see the video here, and you will see now a picture in pictures showing the interface. The real robot is beyond, but at this stage in this short project there was only a simulation environment developed. So you see that you can move around the robot. The robot has a different kinematics than the Geomagic Touch interface, so you have to map this into motion of the end effector. Now you see on the right side that the tip of the needle is entering a first layer of an object, and you see that signals are growing, and in particular there's a large force signal growing until there's a change of material, so you have a sudden drop of the estimated force. And then again, entering inside the object, you will see that there's a various peak of the force, of the estimated force, and these peaks correspond to a change of material. The material are covered by skin, and when you have to enter into the skin, you have to apply a larger force than when you're navigating inside one of these layers. So each, let's say, layer has a skin, and forcing the break of the skin allows to enter in the next layer. And this is what you see. And of course, when you move back, all forces drop down to zero again. So this is a simulator. It's coordinated. It's moved. The robot is moved in the virtual world by the haptic interface. The haptic interface renders the haptic forces that are being estimated in the virtual world through user-defined function. We are not using, in this case, any of the feature of the VREP itself. In the user-defined function, you may also implement, for instance, the residual method. Playing with buttons. This is the right place where to say this. You see on the top right figure, there is now a 3D system device. The logo has changed, where the pen has been dismounted. You see the plug-in, the high fidelity like plug where you can put the pen. Here below I have an expanded view of the pen where you can recognize the dark gray and the light gray buttons that can be pressed by the user while holding the pen. So, playing with buttons. Why is that? Because the master and the slave in general, in particular for the KUKA, have different workspace sizes. If I want to move the end effector of the robot by, let's say, 50 centimeter, of course the KUKA can do this, both in reality and in the virtual world, but 50 centimeter is way too a long distance to remain inside the workspace of the device. Not only there are some configuration of the device where the device cannot return with high fidelity forces. We have seen this in the force workspace defined by the device itself. So although you can extend the device beyond this parallelepiped, at that level the fidelity in rendering the force is no longer good. So, in order to extend the Geomagic limited workspace and to match it with the workspace of a real or virtual robot, a clutching mechanism is required. So, you can make sure that the motion of the hip is transferred to the robot or not. So, when you unclutch the system, you can move around, you can reconfigure the haptic interface without moving the end effector of the robot. So this can be done using the two buttons. In fact, in three combination. There's a fourth one where you don't press the button and you are completely clutched. So you're moving exactly the tip according to how you're moving the tip of the robot or the tip of the needle in this application, according to how you move the hip of the Geomagic Touch. However, if you press the first button, then you completely release the clutch. So the slave position and orientation is modified. Well, this is a negated logic. So if you release the clutch, so you don't press this button probably, or vice versa, I don't remember exactly the detail here, but say with the bottom one, you have you modify both position and orientation of the slave, in our case the tip of the needle mounted on the end effector of the KUKA lightweight robot. Button 2 allows to distinguish between position and orientation. So orientation continues to be modified, but the position is no longer modified. Okay, if you press button 2. Pressing both buttons together, it's like simulating a fixture. In this case, you move only along the position, only along the z-axis, the approach direction of the slave and effect, while the orientation is not changed. So this is complementary to button 2. In this case, when you don't press any button, of course, you can move freely. This is the logic, in fact. You can move freely the pen, and so the hip, and reconfigure the Geomagic Touch device without moving at all the robot. So in this sense, you can recover workspace by not pressing button, and you only when you press 1, 2, or both buttons, you will move completely or partly orientation, or only one direction, or the full position of the virtual agent with which you paired the hip of the Geomagic Touch. Okay, now let's go back to the fact that the child 3D system is becoming obsolete as far as we know. So the idea is to develop a more general solution. So some interface which connects the haptic device both with the virtual world as well with the real world. So this general solution should really both work for the virtual and the real world. So the control entity that you have to design again works as a wrapper, so includes both the APIs of the OpenHaptics libraries in order to communicate with the Geomagic Touch, so receiving, for instance, the hip state and sending the force that needs to be rendered on the device, but wraps also the VRAP remote client, so associate a scene, a tool in the scene, and all the interaction from this, so updating the state of the tool and computing the force in case of contacts, but also may wrap one or more external system proxy to interact, for instance, with KUKA lightweight, or with the universal UR10 robots, or with whatever other system that you have in mind. And the nice thing that if you proceed like this, because you're working with general programming structure, you don't need to edit your code when you do things in simulation, so in a virtual environment, or on a real world, so with experiments. Because the code remains the same, only the communication interfaces and the conversion will be done depending on which is the current target system. So this is a very interesting environment that is being developed in the lab. So if you will eventually do work with these devices and robot devices, or VRAP and the Geomagic Touch on the other side, this is the framework in which you will operate. So in particular, this general solution is made in this way. You have a Geomagic proxy which queries the OpenHaptics libraries and the toolkit, for instance, to update the hip state both in position and orientation, and velocity computed by numerical differentiation typically, And this is in one direction. In the other direction, you need to impose current to the motors, so you need to render the force on the device, and all information being transferred is sent to the high-level classes, which is your specific application-dependent code that process this basic data. The high-level class, of course, interacts either with the on one side with the Geomagic proxy, on the other side with the VREP proxy, so to have an update of the scene, and of course again set and get values for the virtual object in the scene or from the virtual object in the scene to be transferred then into forces to the Geomagic proxy class. Of course, there should be other external system proxy, so library devoted to the specific robot, for instance, that you would like to interact with. And this needs to be developed for the specific cases. Something is already there, some more needs to be done. Just to have an idea of what is inside, there are all C++ or let's say wrapping environments, so HPP code or CPP code that you can, and these are just elementary piece of programs that exist, and it's something the like should be developed. Of course, on the right hand side you see a callback call, so you're passing a code to another program, and then this other program will run this code when it is needed in an asynchronous mode. So let's move to more videos from now on. So I would like just to show what has been developed with the Geomagic and the actual KUKA. This may or may not be the previous system, the child 3D system, or the new programming environment. This makes little difference, but just to have an idea of what can be done in terms of application. So the first application is the creation of a virtual box, so an haptic box around the end effector of the robot. So here you will see moving the end effector of the robot with the Geomagic Touch, so going in any direction, not changing the orientation. And now we create a box. So you will see, pay attention to the motion of the tip of the robot and also to the hip point of the device. You will see that the device will feel a force, and so will stop, in fact, suddenly at the corner or at the side of a box, of a virtual box. Okay? So this has been, so there are two things to understand in this video. In one sense, the command of motion, only position in this case, and this motion is stopped when you reach the limit of a box. At the same time, you feel on the haptic device this force which prevents you to go outside with the hip from the pre-specified box constraint. More sophisticated is a definition of a remote center of motion. This is very important for minimally invasive surgery, where a tool should enter the surface of a human body at a certain point, and this point remains constrained. So the tool inside may still move, but the entrance point constrains the geometry of motion. Okay, this is called the remote center of motion, and you should program this while you progress, for instance, in the insertion of a tool inside the body. You should prescribe that a specific remote center of motion changes its position on the tool but remains constant in the virtual or real world. So here we'll see motion of the tool without remote center of compliance, or assuming that, remote center of motion, or assuming that this remote center is exactly the tip. Now you're moving in position the tip without changing orientation, or by pressing a button you're changing the orientation without moving the position. Okay, so this is the typical situation where the remote center of motion is in fact the tool tip. When you're imposing a different point along the tip, in this case this last aluminium link mounted on the end effector, you see that now you go inside, and now the rotation is close to the tip but not exactly at the tip. You go a little more inside, and now you assign motion in orientation, and you see that you rotate around another point, which is the remote center of motion. And again, you can go even farther. You proceed like this, and now the remote center of motion is in fact very close to the base of the tool, and then you can go back. So I think that this visually explains very clearly what is this. Of course, you have to define this virtual constraint. It's a virtual fixture, in fact, and this is a user code which then interfaces on one side with the haptic device, on the other side with the real robot. So what else could be studied? Well, as such, you can really develop the Navier-Tartenberg parameter, forward and inverse kinematic for your device. Of course, this is inside the system, but you can reproduce this also in your user code, and accordingly the Jacobian matrix, the singularity, the design of PD and PID control, trajectory planning, and various haptic rendering force, and so on and so on. So you can reproduce externally, let's say in a Simulink MATLAB environment, all this concept. If you're too lazy for doing this, you may know that Quanser, which is a brand that produces academic system, let's say like double inverted pendulum, pole in a cart, and so on, has also generated a Omni bundle, so a bundle for the Omni interface, which is another name of the Geomagic Touch, and this interface to a Simulink MATLAB environment. By the way, some of this software is accessible, the part which relates to the interface with the device is not freely available, of course. But at least you can look at what has been done, or amplify, or reproduce, or modify, or generalize what has been done, for instance, by this manufacturer, this software company, in fact. So, what can be studied further? There are a number of very useful applications, mainly in the medical area, but not only. And remember that there's an ongoing development of a software environment for simulating the haptic device to be included in any application. So medical application, here you see a rendering, here you see two KUKA lightweight robot mounting long tools, and these tools are entering in a mock-up of a human body. There's not a real human below, and probably there carrying a remote camera, carrying a remote surgery tool in order to do operation with minimally invasion, so entering only through two small holes in the human body, but operating then inside, after you have performed probably a 3D scan of the patient calibrated the real patient on the surgical table before proceeding. So you can plan the whole operation offline, understand what is the best path, what is the best entry point, and so on, and then do this driven by an haptic interface. Here I will show some results from some student project. So this was needle insertion with force feedback. We have seen first the simulation environment we developed. Later on, this teleoperation was done with the Geomagic Touch and with the real KUKA arm. One of the first things to be set is the definition of frames. And here you see on the right side the reference frame for the master, which is the touch haptic device. You see the blue axis is the z-axis, and this is very convenient because this is looking at the user. We have a base frame also for the slave, which is the robot manipulator, which has at least one axis in the same direction of the z-axis of the haptic device. This is very convenient to give, let's say, familiarity to how you move things. But of course you have also an end effector frame, a tool frame, with a z-axis in the approach direction. So you have to link all this frame together. Then experiments were made with different materials, for instance, interacting with the tool on polystyrene, which is kind of soft but of rigid shape, or interacting with a layer of biological gels, which have a different sense of feeling in the force reaction. There was a force torque sensor, an anti-force torque sensor mounted on the end effector of the robot. You can recognize that beyond the force torque sensor there's a tool plate on which the final tool is being mounted. This could be replaced, for instance, by a needle, in fact, in the medical application. So, how do you control this? Of course, this can be done first in simulation and then on the real robot. The most simple way is this bidirectional teleoperation scheme, in which the master communicates a velocity command to the slave, which is the KUKA. The slave has its own control. In our case, we can use the KUKA controller for generating the force on the slave, and the sensed force from the ATI force torque sensor mounted on the KUKA is fed back to the master. So there are only two channels in this sense. One channel sends velocity commands, and these are realized by the KUKA controller. In the other direction, there are force measurement that are sensed on the slave side, in fact, in the interaction with the environment, and this becomes part of the master control, so of the force that is being generated on the Geomagic Touch device. And the Geomagic Touch device, of course, interacts with the human operator, which applies forces, and the relation between forces and velocity are given by impedance models, as we have seen, or vice versa by admittance model. An impedance model transforms a velocity into a force. An admittance model transforms the vice versa, so a force into a velocity. So this was the basic scheme, but in fact, to improve transparency, one more signal is being transferred. In particular, the velocity of the slave is being returned also to the master. and the control of the master is proportional to the sensed force by again Ks, and in addition proportional to the difference between the master velocity and the slave velocity, of course, of a specific point of the slave, so the tip of the tool mounted on the end effector of the Kuka, and the tip velocity and the hip velocity of the master. Pay attention that the master has no, of course, like many current robots, has no direct measure of velocity. Velocity is measured by differentiation of the position sensors on the master. So Vm comes from measuring the position of the joints and then of the Cartesian point, the hip point, and this is done at the 200 Hertz rate, although the haptic device could also generate data at 1 kilohertz, but we downgrade this in order to be consistent with the 5 millisecond of reliable control of the Kuka arm. And this velocity command, before being passed to the slave, are being filtered. So there's a smoothing part, which is simply an average of the last 3 samples, and a low pass filtering, so that the slave received commands that are smoother. And similarly, when coming back to the master command, so the FMC, the force on the master, the control force on the master, the fact that we are using filtered data makes the behavior more smooth. So eventually a 3-way teleoperation control scheme was used. So here you see the situation where at the end, the final setup, the Kuka mounts a force torque sensor, then a support flange, and on the flange a needle. And the needle is being inserted into a piece of ham. The ham has a thicker skin, and then it becomes softer, as you may know. So in this sense, a teleoperation is being made. Let's look at the video. There's a stop, the approach phase, then the needle enters in contact and now proceeds by pushing inside. And the force feed is sensed on, the force measured is sensed on the haptic device. And this is in one point, then the robot moves to a next point and inserts, and then goes back and forth. Maybe we could go faster here. So I go back and forth to see the motion. You see that how this system operates in real time. So the next step is to move not to a biological tissue like a piece of ham. Here in the lab we are using an abdominal phantom, so still a virtual object, but which has the characteristic real of the central part of the abdomen of a human being, so with ribs, with fat on the surface, muscles, livers, and so on, and also the spine column and a piece of kidney, of the 2 kidneys inside. This pink-like mock-up is being used as a representative of the human body. So the robot is mounting the needle, and at the same time you see that echography is being made of that mock-up. So we will see on the screen of the echograph the needle advancing, so the actual position, driven by a radioscopist, so a medical doctor, using the haptic device, and tracing the reflected force on the device. And the red line that you see in this force diagram, you see first you start with zero force, then the force increases, then there are peaks of variation, and these peaks of variation correspond to perceived or to transition between different tissue until reaching the bone, probably. And the red line are in fact the instant where the user perceived, so this is a more human in the loop consideration, where it perceived some change of contact. And of course it could trace also the evolution of the needle on the echograph, so there is an association, a registration that can be done. And in this experiment, here are more details on the three-way teleoperation control scheme. So when moving from a simulation to a real experiment, here you see on top the human operator. There's a human force which represented here in a block as a step, which is the needle insertion force. So the user needs to, pushes down the Geomagic Touch interface in order to insert the needle. The master is the touch. There's a communication channel with a limited delay. This delay can be the sampling time here, so 5 milliseconds, for instance. And then there's the slave, and the slave is the KUKA lightweight arm. And this interacts with the environment. The environment is still in this case because it's the abdominal mock-up. But if there was a patient, there could be a force due to the fact that the patient is moving because it's breathing. Maybe it's breathing under anesthesia, so it's a smaller breathing, but this could generate another input to the system. So this three-way teleoperation control scheme. The control blocks are on the master. There's a proportional integral controller on the velocity, so if you wish a PD control on the position, but it's implemented on the velocity with parameter BM and KM. On the slave we have a similar definition, and these are the signals that are being transferred in the blocks C1, C2 and C4. The block 3 is not used, and you can see that you're transferring in the block 4 you're transferring a velocity, in the block 1 you're transferring again a velocity, in block 2 you're transferring a force as a feedback to the user. Okay. Now the local controller are in fact exactly like this. On the master side you have a force feedback and a velocity controller, which makes the difference between the environment, so the slave velocity, and the human operator commanded velocity. And on the slave we have a velocity control, which actually we have an impedance control, which generates a force control on the slave side, so the orange FSC signal in response to velocity commands. But since the force control loop is not as good as the position control loop in the KUKA, this has been replaced. So from this commanded force, we generate in fact a velocity. So we reproduced an admittance control on the KUKA robot. So this is the difference between a simulated environment and the real environment. So this is the overall teleoperation control scheme. I was kind of sketchy, but you can look in detail to this equation to understand the rationale of them. And this is the actual result. So here you see on the left top image, you see the echography, and at some point you will see on the top right part of this image entering of the needle. Here you see the needle coming in. You see almost no motion of the robot because this motion is very slow, it's quasi-static. And you see the estimated forces and the user perception by the medical radiologist that detect the various phases. Okay, so experiences transition and bone contact on the abdominal fan. Okay, next, this is a project that has been developed by Dr. Marco Ferro with a group in the University of Naples, where they have a Da Vinci research kit, so a real Da Vinci system, but it's very convenient to have also a simulator, and in fact a portable simulator, so that you can carry with you only the two Geomagic Touch interfaces, a head-mounted display, a screen, and a software code, and this is all you need in order to mimic what happens, to move the robot arm of the Da Vinci research kit, so the Da Vinci RK. What are the characteristics? The Da Vinci is modeled with its own full kinematics in VREP, and this is the first image on the left bottom part of this slide. You have the two Geomagic Touch that emulate the master tool manipulators of the real Da Vinci system, so the way in which you move the real robot through the master of the Da Vinci. These are emulated by the two low-cost, I would say very low-cost, Geomagic Touch haptic interfaces. The teleoperation on the patient side is a task of picking and placing objects. You have contact with the table on which the tools of the Da Vinci robot operates. You use the top and bottom button on the stylus, on the pen of the system, to clutch the system or unclutch the system, so that you handle the kinematic dissimilarity much the same way that we have seen it before for the KUKA lightweight arm, and also to grasp or release object. So the bottom button is used for this. In fact, there's an haptic guidance being implemented, so when you're getting very close to an object, there will be an attractive force that will bring you exactly there before you can do the grasp. So this will ease very much the grasp operation. And similarly, when you're getting on contact with the gripper on the table surface, you will receive a repulsive force, because this is of course an operation that it's not desired. So you see that you can generate virtual constraints that modify the force behavior sensed on the Geomagic Touch because of the actual region in which you are in the virtual scene. And here you will see a short video. This has been developed in full in Sapienza and was presented also at the Maker Fair, both in 2018, in October 2018 and in October 2019. Here you see the various phase, the manipulator are touching object, are touching the table, and when they touch the table, this is felt on one of the two geometric interface. Okay, so this was just a short review. Unfortunately, the best way for feeling this would be to use this in the lab, this simulator in the lab. As soon as this will be possible, we will do that.